the magnetism unit here in AP Physics 2, the dot product and the cross product. And if you've already considered yourself a master on these, please skip ahead to the rest of the video. The dot product, simplified by the big colored in circle, also referred to as the scalar product, because when I do a dot product, the result, my answer, is a scalar, okay? A perfect example is the work energy theorem, where work equals force dotted with displacement, okay? Because this is a dot product, the answer that we get, work, is a scalar, energy is a scalar. We're going to be dealing with another dot product here in the magnetism unit, and that is that the magnetic flux through an area is equal to the magnetic field vector dotted with the area vector. Now, don't freak out. I don't expect you to know what that means just yet, but understand that since we have a dot product here, we know this, the magnetic flux, is going to be a scalar quantity. So often we express a dot product as being the magnitude of one vector multiplied by the magnitude of the other vector multiplied by cosine of the angle theta between them. Which means we no longer need to consider the direction of the vectors, we only consider their magnitude, and we multiply that by the cosine of the angle theta, and theta being the angle that the two vectors make with one another. And therefore, since we're dealing with cosine, our dot product is maximized when the two vectors are parallel to one another. That all stands in stark contrast to the cross product, denoted with a big X, is also known as the vector product, because, as you guessed, when we do a cross product, our resultant, our answer, is a vector, okay? From your mechanics class, we know that the force crossed with the radius vector is equal to the torque vector, okay? Where our answer here is a vector. Torque is a vector, though many of you did not learn it as it being a vector. This, the cross product, is widely understood as the magnitude of one of the vectors multiplied by the magnitude of the other vector multiplied by the sine of the angle theta between them, okay? Such that our cross product is maximized when our component vectors are perpendicular to one another. So when force and radius are perpendicular to one another, sine of theta is at its maximum. The interpretation of the cross product in three-dimensional space is that the cross product finds the vector that is perpendicular to the first two, okay? Here we can express arrows on the two-dimensional plane, but in three-dimensional space, we use the symbol X to describe a vector that is pointing into the page. Think of the X as the hole that the vector makes when it cuts through the page. And we use a circle with another circle in the center of it to illustrate a vector that is coming out of the page, that's coming at you. Think of the circle as like the exit hole of a bullet as it's coming out of the page towards you, okay? So an X denotes a vector that's going into the page. Circle with a circle inside it denotes a vector that's coming out of the page. And I can find a third vector that is perpendicular to those two vectors. And my third vector can be perpendicular to those two vectors either going into the page, or it can be perpendicular to both the vectors coming out of the page, okay? So first, we need to cover what is a magnetic field. Let's look at a simple bar magnet, okay? North pole, south pole. The magnetic field extends outward from the magnet like this, okay? In all directions. It makes a loop of sorts, okay? And the direction of the magnetic field is important. The direction always flows from north to south. All of the magnetic field lines flow from north to south. So if I were staring down the barrel of the magnet, like I was looking at the bar magnet like this, and let's say this was my south pole, then all of the magnetic field vectors would be coming out of the page at me like this, and you would see all of the magnetic field vectors represented around the magnet as such. And of course, they would come out and they would all converge back in through the magnet, where the X symbolizes that they continue on through as such. Where inside the magnet, the vectors flow from south to north, but you will never need to deal with that. The magnetic force is a force that is dependent on the movement of charge. That's why magnetism and electricity are often considered together, because they are so interrelated. That's why we call the force the electromagnetic force. Okay, so the magnetic force can only act on objects that have electric charge. All of the electric charges in the permanent magnet are aligned. Okay? The magnetic force isn't some mysterious new force, it's a derivative of the electric force. So if we look inside the north-south magnet, it's a bunch of tiny atoms that have their polarities aligned, like this, where this is an atom that has plus on the top, negative on the bottom, and all of the polarities of all the different atoms inside the magnet are aligned. Let's take a look at the magnetic force. Okay? On your equation sheet, you can take a look that the magnetic force is equal to QV cross B. And then magnetic force is equal to Q. What does Q represent? Charge. It represents the amount of charge times the velocity of that charge crossed the cross product of that and B, capital B being the magnetic field. From here on out, I'll refer to the magnetic field as the B field, so don't get confused on that. So here's something we've never looked at before, a mathematical representation of the B field. How do we calculate that? Well, you have an equation on your reference table for that. Right at the bottom, you have the equation for B field, that the B field is equal to mu naught over 2 pi I over R. Okay? So this equation right here describes the magnetic field, B field, generated when we have current passing through a wire. Okay? So this is the equation for electromagnetic inductance. That is the word inductance to describe when you are creating a magnetic field using electricity, using an electric current. The magnetic field B decays the further away you get from the wire. So the larger the distance between your measurement point and the wire, the weaker the B field will be. It is important to note how a B field is shaped, okay? And to do that, we use the right-hand rule, okay? Let me say that again. The right-hand rule, okay? I have gotten too many questions wrong because I was using my left hand for the right-hand rule. Don't be like me. Please use your right hand when doing the right-hand rule. Anyway, so there are 2 instances of the right-hand rule, okay? The first instance we're going to cover here. The second instance we're going to cover when we return to the magnetic force equation that we were covering just a few moments ago, okay? This, when we were talking about the magnetic field through a wire, can be illustrated as such. If I have a wire and current is flowing in this direction, then the magnetic field will be created around the wire as such, in a loop. And the loop has a particular direction, as you can see demonstrated by the arrows I am drawing. The magnetic field lines curve in a loop around the wire through which current is flowing, okay? And here is the right-hand rule. If I take my right hand, I open it up, I should align my thumb in the direction of current, okay? That's the step 1. I align my thumb to point in the direction that current is flowing, and then I curl my hand as such, okay? Therefore, the curvature of my hand points in the direction which the magnetic field points, okay? So since my fingers are curving this way, the magnetic field curves this way, such that the direction of the vector is the direction which the tips of my fingers are pointing, as can be seen here. If I illustrate it in another dimension, if I have my electric current flowing into the page, then if I take my thumb and using the right hand rule, I point it into the page like this, which way do my fingers curl? They curve like this, which means the magnetic field curves around like this. Because that is the direction in which my fingers are curling. Okay? That is how we determine magnetic field around a wire. And again, the intensity of the magnetic field decreases as we get further away from the wire. Okay, back to this equation. The magnetic force equals the charge Q times the velocity of that charge crossed with the magnetic field, the B field. Let's give ourselves an example to help illustrate this, okay? I can draw a system right here. And let's say in this system, I have a magnetic field that is going in a straight line out of the page. It means it's coming out of the page at me. So the magnetic field would be illustrated with these circle dots, as I have covered previously. Magnetic field lines are coming out of the page right now. What this tells us is that in order for us to have a magnetic force, we need to have some charged particle, and that charged particle must have a velocity. Okay? Now, again, this is an equation that determines the magnetic force on a charged particle. This is not the equation that determines the magnetic force between two permanent magnets. All right, we're past that point right now. Let's say I have a charge Q. Let's say this is a charge of 1 microcoulomb. Okay, and I got a charge right here, that's 1 microcoulomb. Let's say it has a velocity to the right of 10 meters per second. So let's look at our reference table to determine the units of the B field. Okay, force is a unit of newtons, and the units are kilogram meters per second squared, equals charge, Q, which is units of coulombs, times units of velocity, meters per second, times units of the B field, okay? We have kilograms present on the left side and no kilograms present on the right, so the B field needs to have units of kilograms. Meters are present on both sides. We need to have another seconds in our denominator, and we need to cancel out the coulombs. So these are the units for our B field. Kilograms per coulomb per coulomb second. This unit, the kilogram per coulomb second, is the Tesla, denoted as a capital T. So the strength of a magnetic field is denoted in units of Tesla. Okay? So let's say my magnetic field here is, 10 Tesla. Which, for context, is enormous, okay? Like, usually you're going to be dealing with numbers in the micro or the millitesla, but for the sake of simplifying our calculations, we're going to call it 10 Tesla. The force on our particle by the magnetic field, I should say, is 1 times 10 to the negative 6 times our velocity, v, 10 meters per second, times our magnetic field, B, which is another 10 Tesla, okay? Now, I am moving in this direction. My magnetic field is in this direction. So, these two, my velocity vector and my magnetic field vector, are perpendicular to one another. Therefore, my sine theta term simplifies to 1, because the two are perpendicular. Now I know the magnitude of my magnetic force, which in this case is 10 to the negative 4 newtons, but I don't know the direction how am I supposed to know what direction the magnetic force is operating in? That is where we come into the second interpretation of the right-hand rule. The first one was used to determine the direction of the magnetic field through a wire. This is to determine the direction of the magnetic force on a moving charged particle. Okay? Let's take our right hand, okay, and we're going to open it flat like this, and it's going to stay flat, okay? I am going to put my thumb in the direction of current, like it was before. Hey, Meek, I don't see any current flowing here. This is just a charged particle with a velocity. Yeah, that's the definition of current. Charges moving. So my current is in this direction. Then I want to take my fingers and I want to point those in the direction of the B field, okay? So the B field is coming out of the page towards the camera. So I'm going to point my fingers towards the camera and make sure my thumb is still pointing in the direction of the current, okay? Therefore, the magnetic force vector is the direction in which my palm points. In this case, my palm is pointing directly downward. That is the direction of my magnetic force. Now recall how this is exactly what I was telling us when I covered the cross product. The cross product determines a vector that is perpendicular to the first two, okay? So if I'm crossing a B field with a velocity vector that are both perpendicular in this axis, then my resultant should be perpendicular to the first two, which is going to point down in this case, as we can see. Okay? So that is the most, I'd say, conceptually abstract and difficult to understand part of this. There will be another part, which we will be covering shortly, called Lenz's law, which requires another level of three-dimensional thinking, but don't worry, we're not there just yet. Okay. Before we get there, we need to discuss how magnetic force can not act just on a single particle, but can act on a wire. Because, like I said before, a wire carries current, and this is an example of current. Magnetic force on a wire, again, I'm pulling from the reference table, is equal to the current through the wire times the length, which overlaps the B field, crossed with the B field. And of course, length is a vector crossed with the B field vector. Okay? So let me draw another diagram. Okay? I have a wire with current flowing in the indicated direction, and I have a B field that is pointing upward like this. Okay? Current is flowing this way, B field is pointing that way. Okay? Now, this box that I'm drawing right here, well, technically it shouldn't have the bottom or the top, but this bounded area that I've just drawn represents the area in which the B field is acting, the area in which there is a magnetic field. On this side of the wire, there is no magnetic field, okay? And the purpose of that is I want to illustrate to you that this length vector is not the length of the wire, it is the length of the wire which overlaps the B field, okay? So if this wire was a total of 10 meters in length, I would only be concerned with the 8 meters that overlaps the B field. So in this case, we have current, B field, and force. Let's use the right-hand rule, okay? If the magnetic field is pointing upward, I'm going to point the fingers of my palm upward. I have current flowing to the right, which means my thumb needs to extend to the right. So the force acting on this wire is in the direction of my palm. The force the force acting on the wire is in the direction of the camera, coming out of the page. The force vector is coming out of the page as such. Okay? And I'm sure you all don't need me to review the math. We all passed algebra, we all know how to do multiplication. Okay. So moving on from there, let's try and understand how two wires might act on each other. Okay? First of all, I might have a wire like this, and that wire is, according to this equation, going to generate a magnetic field around it. And the magnetic field, according to the right-hand rule, is going to curve around like this. So it's going to come out of the page on the left side, and it's going to go into the page on the right side, as such. Okay? Right-hand rule. If I have another wire going like this, which has current flowing through it, its magnetic field will be doing the same. Okay? So, since the magnetic field extends eternally but diminishes with increasing distance, it means that at the position of the, I'm going to call this wire 1 and this is going to be wire 2, at the position of wire 2, the B field contributed from wire 1 will look like this. Okay? To calculate that force, we need to first identify that the B field from wire 1 is pushing out of the page like this. The current from wire 2 is moving upwards like this. So I have my thumb in the direction of current, my fingers in the direction of the B field applied to wire 2, and therefore the force applied to wire 2 is going to be in this direction. So the force acting on wire 2 is pulling wire 2 to wire 1. Okay? Now, if I were to reverse the direction of current flow in wire 2, without changing anything else, I would do the right-hand rule again. Magnetic field from wire 1 is going this way. At this time, my thumb should point in the direction of current that way. If the two wires have current moving in opposite directions, they will be repelled. And there's how the magnetic fields of two wires act on each other. Now we can use Newton's third law. Each force creates an equal and opposite reaction. So if wire 1 repels wire 2, it means wire 2 repels wire 1. If wire 1 attracts wire 2, it means wire 2 attracts wire 1, and we don't need to go through the whole rigmarole of calculating the direction of force of 1 on 2, and then to calculate 2 on 1. So, from that, let's move on to a bit more of an abstract concept, magnetic flux, okay? The math is simple, the visualization is not so much. Magnetic flux, if we look at the equations on our equation sheet, represented by the capital Greek letter phi, equals the B field dotted with the A vector. Okay. Magnetic flux, well, what's magnetic flux? Magnetic flux is the amount of magnetic field lines that permeate a two-dimensional area. To simplify that, it's basically how much magnetic field comes through a defined space, okay? Means that if I increase the space, the amount of magnetic field that comes through that space should increase. If I increase the strength of the magnetic field, the amount of magnetic field that comes through a given space should increase, okay? And that's what this equation is trying to tell us. If I were to draw a representation, let's say that the given space I'm trying to analyze is this box, given it's a 2D area, because we are dealing with 2D area in the equation, with side length 4, let's assume it's a square, such that the area is 16, and the B field would be 12 microtesla. My magnetic field were to be coming directly out of the page as such, then my magnetic flux would be maximized. Because remember that the dot product is the magnitude of our two vectors multiplied together, multiplied by the cosine of the angle theta between them. Wait, Meek, how do I get an area vector? that's weird. Area is just a surface. Yes. The area vector is the normal vector to a plane, okay? So if I were to draw the area vector to this square, the area vector would come directly out of the page like that, okay? If the square was laying flat on the table, the area vector would look like that. The area vector is the normal line to the plane, okay? I'd say that the magnetic flux is relatively high compared to further out, when the magnetic field lines become further spaced out, because as the magnetic field decreases, the density of the lines decrease. So if I were to take the magnetic flux through that area, my magnetic flux would decrease because the strength of the magnetic field had decreased as I moved further away from the wire. Okay? Another common point at which they assess your knowledge of flux is when I have an area vector pointing directly up and I have magnetic field vectors that are not parallel to the area vector. We note that the magnetic flux through the area decreases up until the area vector is exactly parallel to the magnetic field vector, in which our flux is 0, because as you can see, there are no lines cutting through the area, right? Which makes sense. If there are no lines cutting through the area, our flux should be 0. Okay, so first up, we have Faraday's law, also known as the law of electromagnetic induction. You don't need to know the names of any of the laws by name. You just need to know the law, conceptually, okay? So what is Faraday's law of electromagnetic induction? It states that a changing B field creates an E field, and a changing E field creates a B field. Changing magnetic field creates an electric field, and vice versa. The law of electromagnetic induction is defined as our electromotive force, epsilon, is equal to the change of the magnetic flux divided by the change in time. Okay? That's the first word right here. A changing B field creates an E field. Okay? So if you have a static B field, the B field that isn't changing, you have no electric field. Okay? Perfect example of that is the permanent magnet. The permanent magnet has a static B field. Okay? If I were to put the magnet next to a wire, and that wire has no current running through it, the magnet will not induce current in the wire. Okay? The B field must be changing in order to induce an electric field. Okay? And for those of you who haven't caught on, if you induce an electric field in a conductor, that makes current. If you induce an electric field in a conductor, that implies a potential difference. It implies a voltage, because current can't flow without a voltage. So I'm going to put big magnitude bars on both sides of this equation, and you'll see why in just a moment when we cover Lenz's law, okay? So, wait a minute, Meek, you said that a changing B field creates an electric field, but I see magnetic flux here. Yes, that is true, okay? In order for you to create an electric potential, you need to have an area in which flux is varying, okay? And the area in which flux is varying must be a closed loop. If I have a B field that's going into the page as such, I can induce an electric field, I can induce a current in a wire that creates an area within the B field, okay? A wire like this would be sufficient, with the closing of the loop would be the edge of the B field, okay? But more commonly, you have a loop of wire that does a single turn within the B field and then exits. So let's consider the much more common example in which the wire enters the B field, makes one complete turn, and then exits the B field, because that's probably how this question will be shown to you on your exam. What does this look like? It looks like an area. What is the area of that loop? Let's say that the side length of the loop is 1 centimeter. Side length of the loop is 1 centimeter, and it's a perfect square. So we're looking at 0.01 meters squared. So that would be the area of our flux shape. So if we were to calculate magnetic flux in this case, given that the B field is 10 microtesla, our magnetic flux, by the equation given to us, is equal to 0.0001 times 10 times 10 to the negative 6, which is 10 to the negative 9, so magnetic flux. And in this case, the area vector is exactly parallel to our magnetic field vector. Of course, you'd plug in cosine with the theta and the angle, and you would get a smaller magnetic flux if the two were not exactly parallel. Okay, if this is static, if this field is not changing, there is no current being induced through the wire. Okay, but if, let's say, I start increasing the magnetic field, if I increase the magnetic field, that will induce a current in the wire, okay? Because now the flux through the wire is changing with respect to time. Why is the flux changing? Because in my B field, in my flux equation, that equals B dotted with A, though my area isn't changing, the strength of my B field is changing. So as my B field increases, my flux increases, and as my flux is changing, I have an induced voltage, okay? Now notice how this is a change in flux. Doesn't specify an increase in flux, which means that the flux could decrease, and that could induce an electric potential, okay? And that's specifically what we're talking about here. We're talking about EMF, we're talking about electric potential. So if my B field went from 10 to 15 Tesla, if I went from 10 to 15 Tesla in a matter of 5 seconds, then the rate of change of my magnetic flux with respect to time would be 1. So that would induce 1 volt in the wire. My electromotive force would be 1 volt. Okay, so that's how you would use this equation. Now, Lenz's law provides us with a different, more precise view on this equation. Okay, where this equation tells us the magnitude of the induced EMF, Lenz's law tells us that the EMF is equal to the negative change in magnetic flux over the change in time, okay? Now, what does that negative mean, okay? A negative means that as the magnetic flux increases, our induced EMF will work to oppose it, okay? Let's dig a little deeper into that. Let me draw a a representation of this diagram on a different side. Okay, so this is my square, which contains my B field going into the page, which would be translated as the B field going downward as such, and therefore my loop of wire would go like this. Okay? We discussed that if there is current flowing through a wire, then the current flowing through that wire will generate a magnetic field, okay? The nature of the magnetic field is the magnetic field really, really likes to stay constant. The magnetic flux really, really doesn't like to change, okay? So if I start to decrease the magnetic field through this area, then the wire will try to increase it. That means that for every action that is taken on the B field applied to the wire will try to undo it. Okay? Now, what does that look like? it means that if I were to decrease the strength of the B field on the outside, and that would be represented by a shortening of the arrows, then the wire will act to compensate, such that the wire will induce a current through the wire, and that current through the wire will generate a magnetic field such that the magnetic field is kept constant through the wire. Okay? If I decrease the magnetic field, the wire works to induce a magnetic field to counteract it. If I increase the magnetic field, the wire induces a magnetic field in the opposite direction to counteract it. Okay? It's basically like saying the wire likes this flux. If you try to increase the flux, the wire says, "Nuh-uh, I liked the flux where it was before," so the wire is going to try and decrease the flux. If you decrease the flux, the wire is going to try and increase the flux, which is what this negative means. Whatever change you induce, the wire is going to do the opposite. So let's take a little zoom in on the wire. All right? Let's say I have a B field going into the page. Okay? Into the page like that. If I decrease this B field, so the B field becomes smaller now, what's the wire going to want to do? It's going to want to compensate for that change. So I decrease the B field, the wire wants to increase the B field. How does the wire increase the B field? The wire needs to generate its own B field into the page. Okay, I'm going to take my right-hand rule for current through a wire, and I'm going to say, okay, my wire wants to add more B field going into the page. So if I add more B field going into the page, it means that my wire will generate current flowing in this direction. That direction, right? Because I did the right-hand rule. So current will flow in this direction in the wire, right? Consequently, if I started with a B field going into the page and I then increase that B field, I make a much bigger B field going into the page, the wire says, no, that's too much. It's going to try and overcompensate by opposing that B field. So how do I cancel out an increasing B field? I generate a B field going the opposite direction. So again, I'm going to take my right-hand rule, and you see what I was doing there? I started using my left hand for a minute. Don't do that. Slap yourself if you do that. Use your right hand and say, okay, the increase was going into the page, so I need to generate a B field going out of the page like this. Okay? So by the right-hand rule, that means that current needs to flow in the direction of my thumb. It needs to start flowing in this direction throughout the loop. Okay? So Faraday's law tells us the magnitude of the EMF induced in the wire, and Lenz's law tells us the direction in which it is induced. The final equation on your reference table is the equation electromotive force, epsilon, equals BLV. Okay? This equation describes the EMF induced when not a loop of wire, but a single straight line of wire moves through a B field. Let's draw the apparatus in which this is observed, okay? You would have two wires, and at the end of the two wires is a resistor, okay? On this side, the wires are open, and on this side there's a resistor between them, okay? Now, there is a B field coming out of the page throughout this area, okay? And I have a stick, a rod, a metal rod, a conducting rod on the two wires, okay? Consider them rails for right now, okay? If I were to slide this rail, slide this rod across the rails, that would induce an EMF in the rod, okay? So let's try and understand how this is working, okay? The equation tells me that the induced EMF in the rod, make that clear, the induced EMF in the rod is equal to the strength of the B field multiplied by the length of the rod multiplied by the velocity of the rod, okay? So if I have a B field of 10 Tesla, a length of 10 meters, and a velocity of 10 meters per second, that means my induced EMF is 1,000 volts, okay? Now you can see why it's so rare to see a B field of strength 10 Tesla. It's really, really rare. Anyway, that means my induced EMF is 1,000 volts, okay? So, EMF in the wire is 1,000 volts, meaning from this end of the wire to this end of the wire, I have 1,000 volts. But that 1,000 volts is going to flow through these conducting lines across the resistor to here, okay? And that is a completed circuit. The magnetic field is forcing the charges in the rod to separate, and it's forcing them to go around this loop to complete the circuit, okay? So let's again use the right-hand rule to look at this. I have a B field that is coming out of the page. Fingers go to the camera. Thumb in the direction of the velocity of my charges. So therefore, the force, the magnetic force acting on the charges is in the direction of my palm, okay? So the magnetic force acts in the positive direction for a positive charge. So a positive charge would be forced downward, but the magnetic force acts in the negative direction for a negative charge, which means positive charges are forced downward, negative charges are forced opposite my palm, upward. So this part of the rod will become positive, this part of the rod will become negative. So therefore current will flow this way around the apparatus. Okay. Again, you guys have questions. You do have questions. Make sure to join the Discord and ask me. Enjoy life.